Yeah.
What a bond now we all have.
That's right.
So it sounds, so the name is
It's in the shape.
it's not as cool as it sounds.
No. It like smells and it's so wet.
I mean, the technology is kind of cool because you basically, it's like cold misting. It's cold misting medicine, right? So you have to put something in that will vaporize easily, but then you hook it up with, yeah, some sort of respirator. Okay, what are we talking about?
So when you like make a matrix out of a,
Oh, exactly what I want to talk about today. Okay.
like, is that basic? Like, we're just, if you take a vector and multiply by that matrix, that is like a linear map, right?
Yes.
Why don't they, I feel like it doesn't make that obvious.
Well, because we haven't gotten to that. I mean, we just skimmed that at the bit. Like I just skimmed that at the end of what I was talking about. He doesn't really make it obvious, but it's I'm going to make it. I'm going to go out of my way to make it obvious. That's what we're doing.
Kind of just like what like the A matrix. Kind of like path, right?
Yeah. So
Linear.
yeah. So I want to. We're sort of at the verge of moving on to chapter 4, which is about polynomials, to give us a concrete library of examples that are not FN to work with. But before we do that, I mean, this is exactly what I want to talk about. I want to talk about what exactly is going on in here, right? Because this is, if there's a place where the wheels come off for people in this class, it's right here, right? Because now we've got all this abstract machinery, and then somehow we're saying, oh, by the way, this is one-to-one correspondence with all this matrix theory at the same time. It's kind of it's like two different parallel things going on simultaneously. So I want to make sure this question you're asking is a useful question, one that I want to talk about. So the first thing, anyway, yeah, I will say that I absolutely do not miss teaching online at all. Thanks. I realized that when I went in and taught, it's like, man, this is awful, sitting in front of a computer doing math. So thanks for putting up with it. There's a chance I'll have to do it again sometime in late May because I got invited to a conference. There might be a couple of days when I'm not here. I'm gonna try to get somebody in class to sub in for those days. Or yeah, yeah. Hi, Sean. Yeah, just come with you. You don't get paid for it. So what I want to talk about today is I kind of want to nail down. We sort of finished chapter 3, but I want to make sure that I completely nailed down the ideas in there because a lot of what we're going to be doing as we go forward in the class is going to involve moving back and forth from matrices to abstract vector spaces. And I want to make sure everybody's clear about what exactly is happening here. So the first big idea of chapter 3 is that any linear operator T, if you have T in L, V, W, I'm just going to put all the pieces together. If you have a linear map from a vector space V to vector to W, and the dimension of V is N, and the dimension of W is M, then there's a transformation, a unique transformation that gives us a matrix of T. And the matrix of T is going to be in M by N matrices. Okay. And this relationship from T to the matrix of T, this is an isomorphism if you choose, once you've chosen a basis. For a given basis V1, if you fix a basis, V1 to Vn and W1 to Wm for V and W, this is a one-to-one correspondence. Every map corresponds to a unique matrix, and every matrix corresponds to a unique map. So that gives us a way of sliding back and forth from abstract linear maps to concrete matrices. And it's a legitimate question actually to ask, well, why do we even bother thinking about abstract vector spaces at all if everything is really secretly finite dimensional matrix theory? There's a couple reasons for that that we'll get to when we get into the polynomial section, but the big idea is that we don't want to throw away any intuition that we get from the space that we're working in. Sorry? This particular matrix isomorphism? Yeah, this particular matrix transformation where we start with the basis and run through by calculating the matrix by applying it to basis vectors. We're going to use that as the sort of standard map that runs back and forth between linear maps in the world of matrices. So the picture that we want, I got asked about so how does matrix multiplication work? So the last thing we did at the end of class was I argued that I didn't prove it, but I made the assertion that the matrix of T times a vector is equal to the matrix of T times the matrix of the vector. Okay. So what does that get us? So the picture I want you to have is this. We have got some vector space V. And over here, I've got a vector space W. And the map that gets us from V to W is the map T. So T is a linear map from V to W. Now V is an n-dimensional space, which means V can be turned into, so any vector in V, so if I have a V in V, that turns into the matrix of V, which is a column vector, C1 to Cn. So a matrix of a vector is a column, right? It's the coefficients of expressing that vector in terms of a basis. Then the map T turns into multiplication by this matrix. And what we're saying is, if TV lives over here in W, right? If I take a vector V and I apply T to it, what comes out is TV. Well, TV is an element of W, it's part of the range, right? And if I do it up here, if I apply the matrix of T to the matrix of V, what this is telling me is I could just multiply those together. Matrix of T times the matrix of V, and what will come out is the matrix of TV. And so these correspond to. So this is kind of the picture that we've built right now, is that we have a way of moving back and forth between vector spaces and the column vectors that represent them, and a vector space and the column that represents it, and that any linear map acting on a vector space can be thought of as matrix multiplication up here. I think this is the question that you're after.
So the matrix of V is just like turning it into like a.
It's turning it into a coordinate vector is the word that gets used here. So in 206, you guys learned about coordinates. Axer doesn't use the word coordinates, but this is one way of thinking about what that is in language that you may have seen before. Everything on the ground. Cover it with chalk. One way of thinking about this is that it's called this is a coordinate vector. And this is a coordinate vector. And the idea is the way that you get from the vector to the vector space is what the coordinate vector is telling you is that the way you get back and forth is in the obvious way, right? That if V is equal to C1 V1 up to Cn Vn, then the matrix of V is just the coordinates that you use to write it down in terms of that basis. So a vector has coordinates as a linear combination. If you take those numbers and write them in a column vector, that's the matrix that represents the vector. And you can go back and forth pretty easily. If you know what the basis is, this just says, take that times the first basis vector and this times the second basis vector and so on. Yep. So you should think here, V is a vector space. T is a concrete map. I mean, it's from a vector space, but T itself is not a vector space. T is a map living in a vector space. It's a function. T is a function, and W is a vector space. So this is the domain of the map T, and this is the codomain of the map T, where the range lives. So T is a function that eats V and spits out a vector in W. Go ahead. Yes. There is, but that starts running up against what Clifford algebras are and tensors, and I don't really want to talk too much about that. But yeah, there is some significance to the fact that the dimensions change. Generally, the way that you get from a one-dimensional vector space to a one-dimensional vector space, or sorry, not 1D, but like a vector space to a vector space is with a map that is that's sort of a two-dimensional array. And if the object here was more complicated, then you would use like a 3 or 4 or 5-dimensional array instead. So yeah, you're asking questions that quickly turn into like Call of Cthulhu type madness, right? So you don't want to look too deep into the heart of mathematics. You might not come out the other side. Yep.
When you were saying you fix a basis.
Yes.
G and W, what about that one?
So you can pick any basis you want for V and W. And as soon as you do that, all of the rest of this is unique for those bases.
But you can just say like,
Yeah, so the thing is, like, I'm saying V1 through Vn because I know any base, I'm just saying any basis you choose, this picture will be determined for you. As soon as you pick a basis for V and a basis for W, everything else that happens here is automatic.
So the linear map is.
The matrix, the matrix for the vectors is unique and the matrix for the map is unique as well. So I'm going to give you a concrete example of exactly what I mean here. So one thing that's come up in the book a lot is differentiation on matrix spaces, right? So I'm going to try two different pictures. So let's think about the derivative map taking 2D second degree polynomials to first degree polynomials. And so that's the D operator right there. Now, if I pick a function, now I have to tell you what the basis is, or none of the rest of this picture makes any sense, right? So let's start by letting P2 be represented as the basis 1z squared. And we'll let P1 be represented in 1z. So there's a basis for P2, standard basis. Here's the basis for P1. So what does D do? I'm going to write down a concrete function that D acts on. I'm going to lift it up to matrix land and show you it's the same thing. So let's just pick a function here, like 1 plus 2z plus 3, how about 1 minus 3z squared. That's a function in P2, right? Degree 2 polynomial or less. What does D do to it? What comes out? If you put in 1 minus 3z squared, you take the derivative. Oh, y'all forgot all your calculus. Minus 6z. Right? Hope everyone's okay with that. Okay, so this is what the derivative operator does. What the matrix transformation tells you is that you could have thought of this up here as the vector 1, 0, minus 3, because that's how you express this in terms of this basis, right? This is 1, 1, and 0 z's and minus 3z squared, which turns into 1, 0, negative 3, which is where that column vector came from. And the D operator turns into the matrix of D, which is equal to 0, 0, 0, 1, 0, 0, 0, 2, 0 with respect to this particular basis. And so what comes out the other side of applying that matrix to this vector? Well, I actually have to do the computation 0, 1, 0, 0, 0, sorry, 2, 0, 0. Wait, is that right? Only like this, right? There, I have fixed it. 1, 0, minus 3. And if you do that computation, you get, well, none in the first coordinate and minus 6 in the second coordinate. What does that mean? This tells you 0 copies of 1 and negative 6 copies of z, which is exactly what came out when you applied the derivative operator. So this vector is the vector representation of that function in P2. So you can either do the operation down here in the vector space, or you can do exactly the same computation up here by studying matrix multiplication instead. Yep.
Can you show it again how to get the matrix for D?
I will be happy to show you because I'm going to give you a different basis and show how it changes the problem next. So where did the matrix come from? So if we're working with the basis, V1 is 1, V2 is Z, and V3 is Z squared, and the map D, and W1 is equal to 1 and W2 is equal to Z, then the differentiation matrix we get the columns of by calculating, well, D of V1 is the derivative of 1, which is 0, which is 0 1s and 0 z's. And I say, okay, so the matrix of D has a 0 and a 0 in its first column, because I've computed these coefficients, and those coefficients become the first row, or sorry, the first column of this matrix. It's the coefficient of W1 after I plug V1 in, and the coefficient of W2. D of V2 is D of Z, which is 1, which equals 1 copy of the 1 function and 0 copies of the Z function. So I use this coefficient and this one because that keeps track of what happened with V2. V2 went in, and the coefficient of W1 was 1, and the coefficient of W2 was 0. And now I plug in B3. E of z squared, which is 2z, which is 0 copies of 1 and 2 copies of z. And so this coefficient, that one, tell me if I put in B3, there were 0 copies of W1 and 2 copies of W2. So with respect to this basis, that's the matrix that represents the action of the function. Okay, so all we're doing here is chasing coefficients. Now I'm going to show you the exact same function. Everything about this function is going to be the same, but if I choose a different basis for P2 and P1, the matrix computation looks different. Okay, it's the same function, but the representation up here changes. So if I change the basis, this picture changes. So let's do the same derivation, but let's pick a different basis to do it. So let's just make this into 1 plus z instead. What if we have the same exact picture? Same picture. But now I tell you, I don't know, for some reason I woke up on the wrong side of the bed and I want my basis of P1 to be 1 and 1 plus z. It's also a basis for P1. These are linear, there's 2 linearly independent vectors in a 2-dimensional space, so it's a basis. This is a basis for P1. So if I do exactly the same thing, I go through this computation, d of 1 is equal to 0, which is 0 1s, and also 0 1 plus z's. And d of z is equal to 1, which is 1 copy of the number 1, and 0 copies of 1 plus z. And d of z squared is equal to 2z. Uh-oh. Well, that turns out to be equal to 2 copies of 1 plus z minus 2 copies of the number 1. Now, hopefully you'll agree with me. I've used the basis elements that this new basis, right? This element right here and this element right here are my basis. That's these elements right here, W1 and W2. But to get 2z, I have to pick different coefficients to get there, right? This function 2z is twice this minus 2 times this. If you do the algebra, you'll see the 2z fall out. So what does that mean about the matrix of D with these bases? Well, now the matrix of D is equal to 0, 0, 1, 0, minus 2, 2. So picking a different basis changed the matrix. You might think, oh God, well, if I change the matrix, maybe I've blown up the whole problem, right? I mean, how could, I can't just put another matrix in there. It doesn't represent the same function. The point is that the representation of the vectors changes too. If you choose a different basis, you're not just changing the matrix of the function, you're also changing the way individual vectors are presented. So in this basis, if I had the function 1 minus 3z squared, well, that's pretty easily still seen to be 1 times the number 1 plus 0 times the number z plus negative 3 times the number z squared. I didn't change the first basis. It's very easy to express this. But when I do this computation, when I come back from the coordinate vector, I'm going to have to change with respect to this new basis instead. So let me walk through how that works real quick. So let's take this out. We still know that taking the derivative of that function is, I didn't change d, right? D is still the same. D still takes derivatives. This map didn't change, right? So now let's put 1 plus z here instead and see what happens. This function still comes up here as 1, 0, minus 3, because that basis didn't change. Now the multiplication turns into multiplication by the matrix 0, 0, 1, 0, was it minus 2, 2? And so what comes out the other side this time should be 0, 1, minus 2, 0, 0, 2 times this vector, which is equal to, oh man, so I have some math to do this time. 0 times 1, so there's a 6 in the first slot, and then 0 and 0 and minus 6 in the second slot. But what does that turn into when you actually turn it back into a function? Well, with respect to this basis, remember these numbers are telling you what to put in front of these vectors. So 6 times 1 minus 6 times 1 plus z is 6 minus 6 minus 6z, which is minus 6z. The answer is still the same. We changed the basis, so this computation changed, but it still represents the same function. This is why we mean you've got to pick the basis that you're doing the problem in. Picking the basis changes the representation, but it doesn't change the function. We still got 6z out. Yep.
The matrix of B is such with respect to the basis.
Yeah, so normally when you say a matrix of D, you also include in that the matrix of D with respect to the basis of B and with respect to W, right? I mean, you shouldn't not declare it. You should always tell me what you're working with. So if you're working with a standard basis, just write down, we're working with the standard basis here. Okay.
What does -6z?
Oh, that's just, it's this, -6z, that was equal to D of 1 minus 3z squared, right? I mean, all I'm saying here is that this coordinate vector can be turned back into, this thing is in F2, right? What I'm saying is I can turn it back into something inside P1 by taking that number and multiplying it by V1 and this number and multiplying it by V2. That 6v1 minus 6v2 turns this coordinate vector back into the function that it represented. So even though it doesn't look like -6z is the vector 6 minus 6, it is with respect to this basis. And a lot of the sort of high art that we're going to be doing here in the end is going to be, how do you jiggle? I mean, a lot of the homework exercises you guys have started, like ask you to do really weird things with the bases, right? Like show you can find a basis that has a 0 in the front, or show there's a basis for which the matrix is all ones and what that means. Part of the reason why you're doing that is to get familiar with the idea that selecting the right basis can put really special structure on the matrix that shows up. So if you remember eigenvalues and eigenvectors, when eigenvalues and eigenvectors exist, it means that you can pick a basis that makes this matrix into a diagonal matrix. And the question is going to be how you do that. How do you find the basis that makes this matrix as nice as possible? Right. So we haven't even started that yet, but that's the anchor that we're using. We're using this to move back and forth between vector spaces and matrices so we can meaningfully make sense of what it means to have eigenvalues and eigenvectors in a generic vector space and not just in like the ones that you learned in 206. That's the big picture here. The reason we're doing all of this is that didn't change, but the representation of it did. And that I can learn about the function D by studying this matrix. So whatever the matrix is holds information about the way that the map acts. Like about, it tells me all about the map. So studying the matrix and studying the map become the same thing. And that justifies studying matrices. Okay. Now I know, so I'll tell you, I got 4 or 5 emails in the last week about people telling me, things are starting to get overwhelming in here and other classes, which of course they are. I'm going to warn you. So first, to the 3 or 4 of you that wrote me about turning in homework late, you're welcome to turn in homework late. No problem. Do it late, that's fine. It's cool. I like to read it. And it's a way of making sure that like you're keeping, you're doing the material you need to do. This is not a good class to get behind in. Because if you're not grappling with this stuff on pace, in 2 or 3 weeks down the road, you're going to look back and we're just going to be using this stuff without talking about it. And if you're 3 weeks behind trying to figure out what the hell I'm doing when I'm talking about eigenvalues, because you don't remember or you haven't worked through the homework exercises where we're transforming back and forth with matrices, that's going to be a lot of work to carry, to pick up. Okay. So make sure if you're getting, like, if you start to slide in here, get yourself caught up because it's only going to keep getting more abstract as we go. And it's going to build directly. We're not changing topics. Everything in this class builds directly on the stuff that came before. Okay. So if you find yourself starting to slide, make sure that you send me an email, like, or no, you don't have to send me an email, just catch up. Come talk to me in office hour, schedule a meeting if you don't understand what's coming on. A lot of you guys are talking to me regularly and Chandra Deep, which is awesome. Make sure you take advantage of those resources. Okay. And I don't want anybody getting lost in here.
Just in terms of proofs on homework and tests, how do we know if we're allowed to do a specific operation, even if Axel hasn't said a definition for, like, for example, derivatives? Like
You can assume any theorem of calculus.
any theorem of calculus,
Yes.
but nothing specifically with matrices, nothing.
You can't use any theorems from linear algebra.
So if we set up something that's a system of equations, but we just set it up like.
So Axler actually, I didn't talk about systems of linear equations, but Axler actually goes through the, that was one thing I meant to mention is that Axler actually walks through how you get from a system of equations and turning it into the corresponding matrix equation. You can just do that.
Okay, cool.
Right? There's no like special art to taking a system of equations and writing it down as a matrix equation. However, you're not allowed to use anything about that. We don't know anything about matrices, right? You guys aren't supposed to know anything about how to compute matrix inverses, if they exist. You don't know about Gaussian elimination. You don't know about determinants. In fact, we won't even learn about determinants in this class. Determinants don't happen until the last chapter of the book. So there's no such thing as determinants. So actually this book, the whole reason this book exists is to teach you about eigenvalues and eigenvectors without ever referring to determinants at all. And if you remember the way that you solved characteristic equations when you were taking 206, you took a matrix A, you subtracted off a diagonal matrix that had lambdas or x's down the diagonal, and then you took a determinant. We're not doing any of that. No determinants. Okay. So, in fact, this is all built off of a paper that Axler wrote called "Down with Determinants," where he said, "Why do we teach math students how to do determinants? It doesn't matter." So this is like the whole theory of the book is determinants come last, not first. But yeah, any theorem of calculus is okay. Any theorem of polynomials. He walks through chapter. So the whole point of chapter 4 is to remind you about the theory of polynomials. Okay. So are there any other questions I can answer before? So I sort of see this, what I talked about right here, is an overview of why we did chapter 3, right? The whole point of isomorphism was to get us to the point where we could slide back and forth from finite dimensional vector spaces into the study of matrices. So if you really want to know like a one-line upshot of chapter 3, so chapter 3 in 2 sentences. Chapter 3, well, I should say 3A to 3D in 2 sentences. First sentence, if the dimension of V is equal to N, V is isomorphic to Fn, and if, here's second sentence, if the dimension of V is equal to N and the dimension of W is equal to M, then LVW is isomorphic to Fn. And then the idea is just, we can work on vector spaces, or we can flip up to thinking about working on column vectors and matrices, like the sort of first quarter linear algebra approach. That's basically chapter 3. It's like a lot of work to get to the point where we can do this. All right.
Okay, so the L of VW is isomorphic to
FMN.
Okay, so does that mean that every linear map from V to W is
Has a unique, once you pick a basis, this is isomorphic to FMN, which means every linear map has a matrix that represents it, and every matrix represents some map. So you have 2 directions there. If you write down a matrix for me, I can tell you the map that it came from. It's unique. Yeah, this is the fact that this is isomorphic means this is unique correspondence, a unique correspondence between a map and its matrix. Once we pick the basis we're working at. Yep.
Does the transpose of MFT represent?
So transpose is an operation we haven't dealt with yet. So transpose is an isomorphism between these maps. Transform gets us an isomorphism from the space FMN to the space FNM. But we got to be careful about what that does to the operators, because the transpose of an operator switches the spaces that it acts on. So we haven't talked about matrix theory yet. So the question you're asking is, what does transpose do? It actually reverses the direction of the map. So it's not the inverse of the map, but if you think about, when we write down the matrix of T, the matrix of T has M columns that represent W1 down to WM, and it has sorry, m rows, and it has v1 to vn columns, right? So this matrix is m by n. If you take a transpose, the matrix that comes out looks like this, right? You've got columns that represent w1 to wm and rows that represent v1 to vn. And so what you get is a map that points in the other direction. It shows you how to do a map from w to v. Okay. Yeah, so that's a deep question. So yeah, A transpose, so you can imagine the matrix of T transpose goes from W to V. This is a really useful fact that shows up later on. So I don't know where we'll get to transposes when we talk about orthogonal projections. All right.
And then is the reason we like care about an isomorphism between V and Fn because like once you get to Fn, it's like easier to work with? Or-
Yeah, you just get a column vector, right? I mean, it means basically you can think about any finite dimensional vector space as column vectors. Yeah, pick your favorite finite dimensional vector space. I don't know, how about the span of e to the x and e to the 2x. Well, those are linearly independent vectors, right? And if I can, on the one hand, I can think about those as c1 e to the x plus c2 e to the 2x, or I could just think about them on the other hand after the isomorphism as vectors that look like c1, c2. And oftentimes this is a much easier way to work than work in sort of general function space sort of thing. Right?
Okay, so e to the x is like a function.
Yeah, I think you're like, this is just some symbol. I mean, this could be the solution to a differential equation if you've seen that before, right? The idea here is like, I could combine, these are not, I mean, is this a multiple of that, a constant multiple of this? Well, no. So as vectors, these are linearly dependent. This is not a constant multiple of that. So I could take linear combinations and have a span. The span is two-dimensional. This is a finite dimensional vector space. These are linearly independent vectors. This is a finite dimensional vector space, but I don't need to think about it as a linear combination of e to the x's, like there's some graph running around. Who cares? It's just two coefficients, one that tells me how many e to the x's there are and one that tells me how many e to the 2x's. So I can work in this sort of gnarly like world over here, or I could just say, yeah, okay, that's great, but why don't we just work with R2? So this move is pretty common in sort of calculus applications as well, to like change problems into linear algebra. In fact, all of the things that are secretly linear algebra turn out to be all of power series. All of power series is really secretly linear algebra. All of Fourier series or Fourier analysis is secretly linear algebra. All of Laplace transforms is all secretly linear algebra. You guys may or may not have seen these depending on the classes you've taken. Everyone in here has seen power series before. But power series are secretly just infinite dimensional linear algebra. And so are Fourier series, so are Laplace transforms. So basically everything is linear algebra. One of the goals of teaching you linear algebra is to secretly convince you that there's no such thing as math that isn't secretly linear algebra. Except if you tell Dave Camp that, he'll yell at you. He's an applied mathematics professor who studies nonlinear mathematics. But then somebody who's an infinite dimensional linear algebraist would say, yeah, well, there's no such thing as nonlinear math because it's just approximated by infinite dimensional linear algebra. So anyway, okay, so that's chapter 3. Everything is linear algebra. That was the lesson. The secret of calculus. What is the secret of calculus? Everything is a line. That's the secret of calculus. Everything that exists is a line. And the secret of linear algebra is that everything is linear algebra. Chapter 4. Before I move on to chapter 4, do we have questions about anything from chapter 3 that I can answer? Chapter 3, this, like I said, probably seems like a lot, these exercises, but I'm giving you the exercises to get you guys to grapple with the idea of moving back and forth between vector spaces and matrices, and to think about the role that the basis plays in getting in the form that a matrix takes. Okay. Anything else I can answer about that before we go on?
When you say like something like a map is invertible and it's unique, what is the inverse? There's like a
If you have there's one of the, yeah, let's make sure we get chapter 3 like completely wired here. So here's the theorem. If T is invertible, T inverse is unique. There's exactly one map that undoes it. So an invertible map has a unique inverse in finite dimensions. We should be careful. Finite dimensional, so maps on finite dimensional vector spaces have unique inverses.
And is there such thing as a basis of T?
Well, T is a map, so it wouldn't have a basis. But yes, actually. So, okay, so it's okay. So how do I find a basis for L of VW? A good question. How do I find a basis for L of VW? Well, is there a space that, let's suppose here, make the assumption that V and W are finite dimensional, so the dimension of these guys is finite. In fact, let's just say it's equal to M and N. And how am I going to do this? So the claim is that this space is actually going to be finite dimensional. I'm going to say the space is finite dimensional, but there's a reason why that's true. Can you think of a space that this is isomorphic to that I've written down twice today already? L from V to W is isomorphic to what? FMN, right? So this space, here, let's use the fancy symbol that means isomorphic. Okay. I meant this. I tipped it on its side by accident. Yeah, it sure looked like an R when I tipped it over on its side, right? Yeah, so a standard symbol that gets used for isomorphic is equals with a little squiggly line on top. Is a symbol that some mathematicians use to mean isomorphic, right? So LVW is isomorphic to FMN. FMN is a space of matrices. Do the matrices have a basis? What is it? Since you just asked me this question, oh, sorry. So this has a basis that looks like, these are called the standard basis vectors in a matrix space. So EJK is a matrix that has zeros everywhere, except for a 1 in one spot in the jth row and the kth column. And everywhere else, it's all zeros. So as an example, if you were in F22, then the basis would be 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. Any matrix in F in 2x2 matrices can be built up by doing linear combinations of these guys, right? So if you want a basis for this, so let's suppose you had an LVW and LVW was isomorphic to F22. Well, how would I get a basis for this space? First off, what would the dimension of this space be? If it's isomorphic to this space, could it have a different dimension than this space? No, they're isomorphic, and isomorphic spaces have the same dimension. How many elements are in the basis for the 2x2 matrices? So what's the dimension of the 2x2 matrices? So what's the dimension of this space of maps? 4. And so what you could do is you could go backwards and figure out what maps. I didn't tell you what the isomorphism was, but if you knew the isomorphism that got you from here to here, you could go backwards and figure out the maps that these came from. Because remember, it's unique, right? So this basis element for F22 corresponds to a unique map over here. And this corresponds to a unique map. This corresponds to a unique map. And this corresponds to a unique map. So if you knew how to do that, you could just write down a basis for this space by just undoing the isomorphism.
And so when you said F22, and it's like a linear combination. So then you add like V1.
Yeah, I mean, you would say C1, 1, 0, everything in the 2x2 matrices can be written like this, right? Because that just gets you C1, C2, C3, C4. So every matrix here can be written as an expansion in this basis.
Okay, and then it's like V1, 2, W.
That's the way to think of, yeah, exactly, right? That lets you get that, right? Because the T that got you from here to here, right? That process of finding the V1, the V2, the W1, W2, you could reconstruct the maps that these all came from. Yep.
So like you said, that each matrix is corresponding to a unique
Yep.
linear map.
Yep.
So
there's a
What-
unique object. So this matrix right here corresponds to some unique thing up here in LVW.
Okay, so what you call that set of 4 linear maps is a basis.
It's a basis for this, yeah.
So linear maps can be basis.
Yeah, if you were a basis here, you were a basis over here. Isomorphism preserves basis. If you're a basis in one space and you undergo the isomorphism, the image of the basis is still a basis. You're not going to destroy linear independence with isomorphism. You can't. If you were linearly independent before you started, you're linearly independent when you come out the other side.
So if that set of linear maps is a basis for this L,
Yep.
then it can span other linear
Uh-huh.
maps.
So basically what we're saying is if you have L of VW, and I say that T1, T2, T3, and T4 is a basis for this space, then I do the isomorphism that turns this all into matrices. Then the matrix of T1, the matrix of T2, the matrix of T3, and the matrix of T4 will be a basis for, sorry, F22. That's embarrassing. Yeah, these correspond to the unique elements. Being a basis of this space is the same as these being a basis for the matrix. Yeah, it's just vector space is all the way down. All right, keep wrestling with it. There's layers here. All right, so now I do want to talk a little bit about chapter 4 here. We're not going to spend a ton of time in chapter 4 on the proofs. I just want to remind you guys about some of the main structural theorems. So this is about the study of polynomials, but because we are working with complex vector spaces, we have to remember things about complex numbers. I don't want to spend a ton of time talking about complex numbers, except to tell you that if you enjoying the way I'm teaching this class and you want to see a more computational version of it, you can come join me in complex analysis in the fall. It's gonna be a good time. Like class I've never had a chance to take before, and a good one. Okay. So Z is equal to A plus IB. That's a complex number. And the real part of Z, real part Z is A, and the imaginary part of Z, imaginary is a really stupid adjective to have used. I don't care about having this recorded right now because I'm going to call somebody stupid, but he's been dead for 400 years. This is Gauss's fault. Gauss is the one who came up with the idea of calling this imaginary number, and then he regretted it. But so this is the imaginary part of Z. Why imaginary? I don't know why they chose the word imaginary, but it sounds better in German. Okay. The thing to note here is that these are real numbers, right? The imaginary part of Z is not the IB, it's just the B. So the real part of 2 plus 3i is 2, and the real part, the imaginary part of 2 plus 3i is 3. I should probably tell you that there's an operation called complex conjugation. So if I write Z and I put a bar over the top of it, I mean A plus IB with a bar over the top of it. What that does is it reverses the imaginary part's sign. It's called the complex conjugate. Complex conjugates take the positive that's in front of the imaginary part, turn it into a negative. Reverse, if it was negative, it makes it positive, reverses the sign. Complex conjugate. That's not much of the stuff I could remind you of, or if you've never seen it before in this language, to convince you of. The modulus or absolute value of Z. So absolute value of Z. And if I slip, I might call this the modulus of Z, which I apologize for, but just in case, I'm going to put it up here just in case. Modulus of Z is just equal to the real part of Z squared plus the imaginary part of Z squared, which if we have the number A plus IB, means that when you take its absolute value, just use the distance formula on it. A squared plus B squared. The reason that we do all this is because most people think about complex numbers as really secretly being like numbers in R2 where A plus IB looks like this, where the A tells you how far out to go in the real direction, and the B tells you how far to go in the imaginary direction. And so the distance that you traveled here is just by the distance formula, Pythagorean theorem.
Yeah, it wouldn't matter what the sign is in the middle.
Nope. Nope. Because you're going to square it. Right. Okay. Complex numbers are awesome because they do all the algebraic things that you want them to do. There's a whole list of algebraic properties that I want you to take a look at, which is on page 4.5. There's an entire pile of them. They just mean how you do arithmetic with them. One of the most important ones that shows up is that if you take z and you multiply it by its complex conjugate, that's a plus ib times a minus ib, which is a squared plus iab minus iab minus I squared b squared, which is a squared plus b squared. Because remember, I has the property that the square of I is -1. So what does that mean? Well, this is the length of z squared. You took this formula and you squared it, the square root will go away, right? So z times z bar, this is sometimes referred to as z bar. Again, if I slip, I won't mean to do that. I am a complex function theorist by trade, so sometimes I slip into the language without meaning to. The important thing about complex numbers is that you get this absolutely wonderful theorem called the fundamental theorem of algebra. The first thing I want to note is, so here's the first big theorem, which is a polynomial is uniquely determined by its coefficients. So what I mean by that is if I give you a polynomial and I tell you that if I tell you the coefficients, there's no other polynomial that's the same polynomial. Each polynomial corresponds to precisely one set of coefficients. This is actually implied by the isomorphism theorem. Right?
This almost seems like it's just like numbers are unique. Like, because if a
Well, I mean,
polynomial
the
is
idea here is that, like, imagine you wrote this down: a naught plus a1z and plus up to an cn is equal to 0. If I tell you that statement is true, what can you tell me about the a's? Why? It's a basis for the space of polynomial, right? So we can actually prove this by asserting that, well, since 1 to zn are a linearly independent set, or they're a basis for pn, then the only way this equation can be true is if all of these coefficients are 0, and that means 0. This polynomial is, the 0 polynomial is uniquely determined, which means every other polynomial is 2. Okay, so the argument for this runs through the assertion that this equation must have a unique solution. I welcome you to read that argument. The point is, and the big thing that we want to go for here is a fact I've already been letting you guys use for free. I'm just setting the stage. We're going to go into more depth on this next time. But I'd like you to read chapter 4. It's just, there's no sections in chapter 4. It's just chapter 4. And the culmination of the whole thing is that if you have a polynomial in, if you're an element P in the polynomials on the complex numbers, every polynomial with complex coefficients has a linear factor. Then P is equal to Z minus C times P tilde of Z. Every polynomial with complex coefficients has a linear factor. Is that true in R? Well, let's see. Why are complex numbers better than real numbers? Because in complex numbers, this thing is equal to this. That factors. You guys never learned like a sum of squares formula, because to have a sum of squares formula, you need to know complex numbers exist. There is a sum of squares formula. It involves I. In the real numbers, so this is over C. If I think about this as a polynomial with complex coefficients, I can always factor it down to linear terms. If I'm over R and I get Z squared plus 1, well, I'm done. We get to use the embarrassing word irreducible. And you'll even remember that when you learned the theory of partial fractions in calculus, there was a whole lot of shenanigans that happened over irreducible quadratic factors. Wouldn't it have been nice if they taught you complex numbers and so everything could be written like this and all of that horrible systems could have been avoided? So the idea is the real numbers are hard by comparison. It's going to turn out vector spaces over real numbers are hard by comparison because things don't factor all the way down to linear terms in real numbers. And they always factor down to linear terms for complex numbers. And we'll go into more detail the next time. So read chapter 4 and keep working on your homework. And I will talk to you guys. Oh man, I don't get to see you again for another like 4 days. Well, I'll be on Slack